The James Webb Space Telescope, or JWST, has become a cosmic time machine. Its advanced infrared instruments penetrate the vast distances of space, allowing astronomers to observe the universe as it appeared billions of years ago. These unprecedented views are now delivering data that challenges fundamental assumptions about cosmic evolution. Recent observations are forcing astrophysicists to confront a profound enigma: the existence of unexpectedly massive and mature galaxies in the very early universe, a mere 300 million years after the Big Bang. This discovery is not just an incremental finding, it represents a direct contradiction to established cosmological models, initiating a widespread re-evaluation of our universe's history. Astronomers, led by Dr. Erica Nelson of the University of Colorado Boulder, reported in a 2023 Nature Astronomy paper the detection of 6 candidate galaxies. These galaxies exhibit stellar masses far greater than theoretical predictions for their epoch. Located at redshifts ranging from z equals 7.5 to z equals 9.1, these objects appear fully formed and mature, raising immediate questions. According to Dr. Garth Illingworth from the University of California, Santa Cruz, these galaxies are too big, too early, and too organized to fit the prevailing cosmological narrative. This direct observational evidence creates an immediate tension with the standard model of cosmology. The standard cosmological model, known as Lambda-CDM, dictates the universe's evolution. This model posits that the cosmos began with the Big Bang, followed by a period of rapid expansion. Galaxy formation within Lambda-CDM is a hierarchical process. Small structures form first, then gradually merge and grow into larger galaxies over billions of years. According to this framework, galaxies in the very early universe should be relatively small, irregular, and actively forming their first stars, not massive and well-developed. The model sets strict time constraints on how quickly matter can coalesce and stars can form. The observed galaxies appear at a cosmic age of just 300 to 500 million years after the Big Bang. For context, the universe is currently estimated to be 13.8 billion years old. This narrow window of cosmic history allows very little time for galaxies to accumulate the vast amounts of mass observed by JWST. Dr. Peter Van Dockum from Yale University describes the problem, stating that these objects would have had to form stars at an extremely high rate from almost the moment the first stars ignited. This timeline presents a significant challenge to the conventional understanding of galaxy assembly and stellar evolution rates in the early cosmos. The newly detected galaxies boast stellar masses estimated to be tens to hundreds of billions of times the mass of our Sun. For instance, the Glass Z13 galaxy, one of the earliest confirmed, shows evidence of a significant stellar population. To reach such mass in a few hundred million years, these galaxies would need to have converted gas into stars with astonishing efficiency, far exceeding expectations. Dr. Joel Leha, an assistant professor of astronomy and astrophysics at Penn State, highlights that the sheer mass observed implies a formation process dramatically different from the slower, more gradual buildup predicted by simulations based on Lambda-CDM. Beyond their immense mass, these galaxies also exhibit signs of maturity. Spectroscopic analysis suggests that their stars are not all freshly formed, many appear to be older, having completed several star formation cycles. This implies a prolonged period of star-making activity, commencing even earlier than the 300 million year mark after the Big Bang. Professor J. Stuart B. Wythe of the University of Melbourne points out that such mature stellar populations challenge the accepted timeline for the cosmic dawn, suggesting that the era of first star formation might have occurred much earlier or been far more intense than previously modeled. This pushes the boundaries of our chronological understanding. The distance and age of these galaxies are determined through their redshift. Light from distant objects is stretched as the universe expands, shifting towards the red end of the spectrum. Higher redshift values correspond to greater distances and earlier times in cosmic history. JWST's instruments are uniquely capable of detecting the highly redshifted infrared light from these ancient galaxies. Observations by the SEWER survey, for example, have identified galaxies with redshifts up to z equals 16, pushing the observational frontier closer to the Big Bang. This robust data confirms their immense distance and thus their existence in the extremely early universe, reinforcing the observational anomaly. Multiple international collaborations using JWST data have reported these findings. Key among them are the Cosmos Webb program, which aims to survey an unprecedented area of the sky to detect early galaxies, and the CERS, Cosmic Evolution Early Release Science, survey. The GLASS, Grism Lens Amplified Survey from Space, program has also contributed crucial spectroscopic confirmations. These independent teams, employing different observational strategies and analysis techniques, consistently arrive at the same conclusion: galaxies are forming much faster and becoming far more massive than anticipated in the earliest epochs. This convergence of evidence strengthens the argument against the Standard Model's predictions. In the Lambda-CDM model, dark matter halos are the gravitational anchors for galaxy formation. These invisible halos accumulate first, then draw in baryonic matter, ordinary gas, which cools and forms stars. The challenge for these early massive galaxies is that dark matter halos themselves also take time to grow. For such massive galaxies to exist so early, the corresponding dark matter halos would need to have assembled extraordinarily quickly and efficiently. Dr. Risa Wexler, a professor of physics at Stanford University, states that the sheer abundance of massive dark matter halos required by these galaxies is inconsistent with current dark matter simulations. This creates a significant gap in our understanding of early cosmic structure formation. To reconcile these observations, astrophysicists are exploring mechanisms that could accelerate galaxy growth. One hypothesis suggests that the early universe might have had conditions more conducive to rapid star formation, such as denser pockets of gas or more efficient cooling mechanisms that allowed gas to collapse into stars faster. Dr. Brant Robertson from the University of California, Santa Cruz, proposes that if the initial conditions of the universe allowed for a higher density of primordial gas, or if the feedback processes from early supernovae were less disruptive, galaxies could have accumulated mass at an unprecedented rate. This would require deviations from standard assumptions about the properties of early cosmic gas and stellar feedback. Another angle of investigation involves the fundamental constants and parameters within the Lambda-CDM model. If the universe's expansion rate, described by the Hubble constant, was different in the very early cosmos, or if the properties of dark energy or dark matter varied, it could alter the timeline for structure formation. Some researchers are probing whether a slightly different cosmological constant could allow for earlier galaxy growth. This area is highly speculative but underscores the gravity of the challenge posed by JWST's data. Dr. Subir Sarkar from Oxford University has long advocated for testing the limits of standard model parameters, suggesting that discrepancies like these may point to subtle variations. One radical, yet increasingly discussed, possibility is that the universe is simply older than currently estimated. If the Big Bang occurred further back in time, it would provide more cosmological time for these massive galaxies to form and mature. This would imply a revision of the Hubble constant, which dictates the universe's expansion rate and, by extension, its age. Professor Avi Loeb of Harvard University has been a prominent voice exploring such possibilities, suggesting that anomalies like the JWST galaxies compel us to consider alternative timelines. While highly controversial, this hypothesis would naturally resolve the time-too-short problem for early massive structures. Another intriguing, albeit speculative, theory involves primordial black holes. These are hypothetical black holes that could have formed in the very early universe, even before stars. If a significant number of these primordial black holes existed and were sufficiently massive, they could have acted as seeds, rapidly accelerating the collapse of gas and dark matter to form galaxies. Dr. Julian Krolik from Johns Hopkins University has explored the conditions under which such black holes could act as gravitational attractors, potentially explaining the rapid assembly of mass. This mechanism could bypass some of the time constraints imposed by standard hierarchical formation, offering a pathway to early, massive structures. The tension between JWST's observations and the Lambda-CDM model is not isolated. For years, cosmologists have grappled with the Hubble tension, a discrepancy in the measured expansion rate of the universe. This new evidence of early, massive galaxies adds another layer to this foundational challenge. It suggests that our understanding of the universe's infancy, or its fundamental properties, may be incomplete. Dr. Wendy Friedman of the University of Chicago, a leading expert on the Hubble constant, emphasizes that observational anomalies demand careful re-examination of our theories, not just minor adjustments. The universe appears to be more complex than our models currently describe. The sheer volume and quality of data from JWST continue to flow, providing unprecedented detail. Each new deep-field image and spectroscopic analysis brings further clarity, but also new puzzles. Upcoming observations will focus on obtaining more precise spectroscopic redshifts and internal dynamics of these early galaxies. This will allow astronomers to confirm their masses, star formation histories, and chemical compositions with greater certainty. Dr. Sandra Faber of the University of California, Santa Cruz, underlines the importance of this ongoing data collection, stating that while the current findings are compelling, a full picture requires extensive follow-up to solidify the initial observations. This ongoing scientific challenge exemplifies the dynamic nature of cosmology. Discoveries that contradict established models are not failures, but opportunities for profound advancement. The initial excitement and debate surrounding JWST's findings are healthy signs of a vibrant scientific community. Researchers are now actively working to either modify the Lambda-CDM model to accommodate these observations or to explore entirely new frameworks. Professor Priyangvada Natarajan of Yale University notes that this is precisely how science progresses, by pushing the boundaries of what we thought we knew and adapting our understanding based on new evidence. It is a period of intense re-evaluation and innovation. The James Webb Space Telescope has opened a window onto an early universe far more complex and evolved than previously imagined. The existence of massive, mature galaxies just 300 million years after the Big Bang fundamentally challenges our standard cosmological timeline and the models built upon it. Whether this necessitates an adjustment to the rate of cosmic expansion, a revision of our understanding of dark matter, or a re-evaluation of the universe's true age remains the central question. What is certain is that astrophysics is at a pivotal moment, with new data forcing a rewrite of cosmic history. This debate underscores the power of observation to push the frontiers of human knowledge.